Welcome to the Cosmic Pie Podcast, episode number 38. I'm your host, Wayne Barkhouse, and with me, as always, is
Robert Moore.
So, Robert, we are broadcasting from the campus of the University of North Dakota here in Grand Forks.
Yep.
And
Beautiful place.
Beautiful place. And most of our snow melted.
Yeah, all our snow melt. I don't know what's up with that.
Isn't that amazing?
Yeah.
But you know what's going to happen. It's just making room for new snow that's going to come
let's
here
not talk
eventually.
about that. As long as it doesn't happen around Christmas.
You need to travel at Christmas.
I need to travel. Yeah.
Yeah. Well, if you have any questions during the podcast, feel free to ask them or any comments that you might have using our chat feature. And also, as a disclaimer, anything that any of us says, our own personal opinions, and not necessarily those of the University of North Dakota, nor the College of Arts and Sciences, nor the Department of Physics and Astrophysics. Now, today, Robert, we have a very special guest.
Absolutely. Yep.
And our special guest is Hayden Drow. Now, as a disclaimer, I'm going to say that I am a co-advisor to Hayden. He's doing his PhD here in our department with myself and Professor Tim Young. And so with that, I'm going to turn it over to Hayden to do a more in-depth introduction. And Hayden, thank you very much for being here today.
Thanks for having me. Like Dr. Barkhouse said, I am a physics PhD student here at the University of North Dakota, working with Dr. Barkhouse and Dr. Young, and we are simulating the merger of binary neutron stars. So kind of my area of research is general relativity and gravitational waves and everything that entails.
Now, Hayden, you mentioned general relativity.
Yep.
And pretend that you're on a plane, let's say, flying somewhere, and there's like a politician sitting beside you, and he's a member of Congress, and you're looking for federal money to support your research, and he doesn't have a physics background. How would you describe what general relativity is all about to somebody like that?
I just have to pause because what is the best way to describe it to try to get money?
Well, try it in simple terms, not necessarily the money aspect. Just how would you explain GR to like a lay person? That's what I'm asking.
The best way I could describe it is GR is our current best understanding of gravity. It is kind of I don't know if I should call it a generalization of Newton's laws, because Newton's laws kind of break down once you actually start getting towards big objects and objects that are moving quickly. So it is kind of a continuation and an extension. And the way GR works and propagates gravity is not really through a force like gravity does, but it's through the warping of space-time, because special relativity taught us that space and time are not actually two distinct things. They're kind of combined together and mixed together into this one thing called space-time. And general relativity kind of takes that idea of space-time and mixes in gravity and shows that gravity is actually caused by the warping of space-time.
Okay.
So from the point of view of Newton, Newton then would have suggested or at least described gravity as a force between two objects that have a mass, correct?
Correct.
And so in time itself, according to Newton, would have been absolute. So the time that elapses on your watch, for example, if you had one, or the time elapsing on a watch from somebody who's on a planet, let's say orbiting Proxima Centauri, a little over 4 light years, that 1 second for them, a time interval 1 second would be 1 second for you. So there'd be no difference in the elapse of time.
Correct.
So, and then Einstein comes along and he, if you like, changes all of this. And the special theory of relativity, which was published in 1905, and then general relativity itself came along basically near the end of 1915, and then I think officially published in 1916, if I'm not mistaken.
I think so, yeah.
But he was given talks on it in late 1915. He upsets everything and making suggestion that time is not absolute in that sense. That time is malleable, if you like. It's flexible. It depends on the relative motion of people that are going by you, let's say locally. Mm-hmm. And therefore, there's not this fixed absolute time, this grand cosmic clock that clicks away every second that times the universe in that sense. That time can be different depending on the situation, where a person happens to be located relative to you, how fast they're moving, all of those things.
And I like the way you phrased that he upset things, because he upset things and people with this view of things.
So, hey, do you want to describe a little bit of the effect of time itself? So, what would happen to time? Let's say if you were somewhere, I don't know, let's say 1 light year away from me, and you're in your spaceship, and before you left to go on your journey, we synchronized our watches, and I stayed here on the Earth. Now, what would happen to my time relative to your time?
Well, assuming that one of us is actually traveling toward or away from each other, both of us would see the other person's clock ticking at a different speed. So, for example, if you're stationary there on Earth and I'm floating away somewhere else, you'll see that it looks like time actually slows down for me.
Now, what happens if you're stationary relative to me?
If both of us are stationary, we should measure the same ticks in time.
Well,
the only difference then would be whatever gravitational body is around us. If you're actually on the Earth and I'm, say, there's nothing else around and I'm orbiting at a point way higher above the Earth, then you would actually experience time slower than I would, since gravitational attraction or gravity also causes time to vary speed.
right, so the presence of mass, in this case, we'll just use the Earth as the mass, that presence of mass warps or affects space and time, so space-time.
Right.
And it affects it in such a way that if I'm standing on the surface of the Earth, and if you compare it to somebody that could be stationary, a certain distance away from the Earth, there's no other object around them, then time for me would slow down relative to that person. It would elapse at a slower rate than the other person that's further away from the Earth than I am.
Now, Earth's a pretty small body as far as mass is concerned, so I'm like, let's get into just how different it is, how much difference we're talking about, because it really should be just like nanoseconds between Earth's surface and even, say, the moon, right?
It is small, but not immeasurable.
Right. Because
atomic clocks are accurate enough now. I believe it's about a centimeter height difference that they can actually measure the difference in time delay.
Wow. I knew they had to take it into account for GPS satellites, but I wasn't aware that they'd gotten them synchronized that well.
Well, okay, so Hayden, have you seen the movie Interstellar?
Yes, I have.
Okay, so for those of you who have seen the movie, or maybe you will in the future, do you remember one of the premise in that movie is that you have astronauts that went down to a planet which was orbiting a black hole, a supermassive black hole. And there were planets closer to the black hole and some planets that were further away. And that for you being on the surface of a planet that was deeper inside the gravitational well of a black hole, time elapsed at a much slower rate than a planet that was much further away. And so back on Earth, of course, we were at the point where I think it was the difference of 1 hour standing on this particular planet that was close to a black hole would actually be equivalent to something like 7 years elapsing back on Earth.
Yep, if I remember correctly, that's about what it was.
Yeah, so then people on this planet got into a little bit of a situation, and it took them several hours to get off the planet. And then by that time, like 21 years or so had elapsed back on the Earth.
Yep.
And so that time difference actually can be extreme depending on the arrangement. In fact, you mentioned, or Hayden mentioned the fact that with atomic clocks now, we can measure differences of about 1 centimeter in height above the Earth and look at the time elapsed difference. I think there was something, Robert, wasn't there something recently within the 12 months that they used some type of atomic transitions, which is different than the atomic clocks that they're using, where they actually detected, I thought, like height differences on the scale of millimeters, even smaller than
I don't know.
centimeter.
I'm surprised to hear centimeters.
Yeah.
I do know that they've gotten using interference techniques and atomic clocks that they can measure time down to like attoseconds,
Right.
you know, which atto is 10 to the 19th,
Yeah,
Or
I
10
don't
to the 18th,
remember. Yeah.
minus 18th, I should say.
Right.
And so we've got clocks that can tick to very high precision. So it doesn't surprise me now that I'm thinking about it that we can measure time dilation on the order of 1 centimeter altitude change. We do have a question or a comment from Bill Schwalm. Why wouldn't it work to explain gravitational waves if you just included time delay in a scalar Newton kind of gravity theory?
And we didn't get into gravitational waves yet, so
Right.
let's hold off on
So
that.
let's hold off on that one, Bill. We'll get to you in just
Yeah.
a second.
So okay, so the time, and people might, there's people out there that say, why should we do this type of work, this research into fundamental physics? Obviously, there's an interest point of view. If one wants to understand how the universe works, one wants to do this type of research.
Right.
But there's even practical applications that on the surface may not seem useful in the beginning. For example, you may get someone like the person, let's say Hayden, that's sitting beside you on a plane, a politician, a member of Congress, and says to you, well, the work that you're doing on the general theory of relativity, how does that make gasoline cheaper? So it costs less for the average American to fill up their car. And you'd say, well, nothing, right? There's nothing I'm doing. But, because of the special and general theory of relativity, it allows the average American to go on a cross-country trip in the summertime and not get lost because they can use the GPS system.
Right.
So Hayden, do you want to explain a little bit what the impact of relativity is for the GPS type of system that we know and love today?
So yeah, the impact on the GPS system is actually twofold. I forget which one is actually the stronger dominating one, because you've got the satellites orbiting around the Earth and they're orbiting at some high speed, and that will actually cause the satellites their clock to tick slower, so they will not go the distance that they expect it to go during that amount of time. And then you've also got that it is farther away from the Earth, so that should cause the clocks to tick faster. And I don't remember which one is actually dominating. I think it's general relativity is the one that dominates, so their clocks are ultimately ticking slower. And I don't remember exactly how much it's off by, but if you didn't account for that, I think the GPS system would be off by something about 1 kilometer per day. So really you would have any type of GPS guidance system, because you could never get an accuracy better than 1 kilometer, or your accuracy of 1 kilometer can't really last for more than a day. After that, it's just going to completely drift out and you're going to lose all your precision.
Right.
Right, so you're on a trip on your way to New York City. If you wind up in Philadelphia,
In Philly. Right.
then you know what happened.
Right. Because I'm going to, put it into freedom units for, our American audience. Kilometer is going to be a little over half a mile. So without taking into account general relativity and the slowing of the clock ticking, you're only accurate with GPS to half a mile roughly.
And that error accumulates.
It accumulates,
So
right?
it gets greater and greater and greater with time until eventually it becomes useless, like the system,
Right.
right?
You would constantly be having to recalibrate it to the position of the satellites.
Right. In fact, when the engineers first turned on the GPS system, they did find this was happening.
Mm-hmm.
And they actually went to the scientists, physicists, and asked them, can you help us here? And you can imagine a physicist saying, well, did you take into consideration relativity? And they're like, what's that? And so the answer is no, obviously. And I'm sure that's not what happened, but that's kind of, like
It's probably closer
an
than
urban
you
myth.
think.
But anyways, once you take in relativity into consideration, as you mentioned, Hayden, both special relativity and the general theory of relativity, then we have the GPS system that we have today, which
Right.
can be very accurate, especially if you're using military type purposes.
If you turn on that military system, I've worked with it, and you can get down to like centimeter precision. So
Yeah, so it's amazing. But
It's
it's
incredible.
but it's all based on the fact that you need relativity. Someone needed to do that fundamental research in the beginning and allow us to have the things we have today. So it's almost saying, what's that research that you're doing now? What use of it? Well, what use is a newborn baby?
Right. As
Michael Faraday.
Michael Faraday once asked.
Yeah. So, so from that point of view, so Hayden, when you think about the general theory of relativity, one of the things that's been cropped up in the news media in the last several years is the discovery for the first time, this initially happened in 2015 and reported in 2016, is the detection of gravitational waves. So there was a lot of bluster about that at the time for good reason. But can you explain a little bit about gravitational waves, what they are all about, and how does the general theory of relativity fit in with that?
So the best way I could describe gravitational waves is, so just like general relativity was that curvature of space-time. So we've got this one thing, and the way people like to imagine it is something like a sheet where you've got a mass and it distorts space-time. It will sit there, distort the area around it, and things will be drawn in on the sheet. You can also have ripples on that fabric, just like you can have ripples on the pond of a lake or on the top of a lake or something. So it is those ripples that you would actually see in space-time that are the gravitational waves that we can measure.
Right, so I guess an analogy you could use is you can envision, let's say, a trampoline in your backyard, and nobody's on the trampoline, and the surface of the trampoline, that's 2 dimensions. And we're not worrying about the thickness, of course. Think of it as a 2-dimensional structure, and it's nice and tight or taut. And if somebody stands in the middle of the trampoline, you can clearly denote or detect the curvature around that person where they're standing. In fact, if they're standing in the exact middle and you look off to the corners of the trampoline, that could be nice and flat. It's just curved, noticeably curved, where the person is standing. So you could use that analogy and think, well, with the presence of mass, and you look at space-time around that object, then that space-time is also altered, like space is curved around that object, like the person standing in the middle of a trampoline, and the surface of that trampoline would be curved near where they're standing. But imagine if they were jumping up and down. Then you'd have this rippling effect that would move outwards from the center of where they are moving up and down, and it would be waves in the surface of the trampoline material that would propagate outwards in all different directions. And that person moving up and down, in this case, you can think of it as the inspiral of 2 dissimilar masses.
That's what I was about to ask, because if I just have one mass on that sheet, if I have it moving around, it's not going to produce any of those ripples. It's just going to produce a dent that rolls around, moves around with it. So it takes 2 objects of unequal mass to produce those ripples.
It actually just has to be an object experiencing some type of acceleration.
Okay.
So you could have a single object, if you were accelerating it some way, that would still produce gravitational waves. So even if you've got like the example of an electron in an antenna oscillating back and forth, we know that will produce electromagnetic waves, but also to a much smaller extent that will also produce gravitational waves. But gravitational waves are so much weaker than electromagnetic waves, there's no chance of really ever measuring something that small, oscillating that slowly, for really lack of a better term, because also objects have to be orbiting very quickly to produce gravitational waves, or rather accelerating very quickly to produce gravitational waves, orbiting just being another type of acceleration.
Okay.
Yeah, but in fact, anything that rotates that's not perfectly symmetrical, like the Earth, or like an object that has, let's say, a mountain on it. So imagine it's a perfect sphere, except there's a mountain in one location. That object alone rotating, that's going to produce gravitational waves.
Okay. That's kind of neat to think about, that you've got to have not just some mass, but you've got to have some kind of disturbance on the mass itself to get these waves propagating away from it.
Asymmetry, as we would say, right?
That's the term.
In fact, with the detection of gravitational waves, when people look at this, they can actually put some constraints on how out around a certain object is. In this case, I'm thinking of a neutron star. Now, we'll get into neutron stars in a minute here. But a neutron star is the leftover remains of the collapse of a massive star. And the neutron stars would have a mass less than about 3 times the mass of our sun. If they had more than that, they actually collapse to form a black hole, which we can also talk about today. But for a neutron star, you can think of an object that's extremely dense. So it's like 1,000,000,000,000 times denser than the Earth. And it's rotating rapidly, and it has a size on the order of roughly 20 kilometers in diameter, about 10 miles in radius. If there was any type of asymmetry in the overall shape of that object, so it's
Oh,
so it's
wow.
aspherical, it'll generate gravitational waves, and if it's outer round enough, if you like, it will generate gravitational waves such that we can detect it with the instrumentation we have running
So
today.
that's how they did that.
Yeah, so they can actually put upper limits on how out of round, I should say, neutron stars are in a couple different locations. And we
Right.
find that neutron stars, it's like where a neutron star is like 20 kilometers in radius, there can't be any outer roundness, any height on the surface of the neutron star that's higher than the width of a human hair, or that would have been detected through gravitational wave emission.
That's crazy.
And you might think, how is that possible? These things are so dense and so compact and squeezed in such a small volume of space, such a massive thing, that in fact, we can't make a sphere that perfect here on Earth with our technology. Neutron
Yep.
stars are closer to being the perfect sphere than what we can manufacture artificially today.
Yep. It's crazy, but yeah, that makes sense now. But again, it's because of the exotic nature of neutron stars, folks. They're, take a star 3 times the size of our sun and compact it down into something the size of Grand Forks, a small city.
Well,
And-
I was going to say, here's an example of how bizarre they are. You ready for this?
okay.
And this actually comes from Jocelyn Bell Burnell,
Okay.
who was actually a person who discovered pulsars in the 1960s, which ultimately we realize are coming from neutron stars, actually neutron stars.
Right.
And what she likes to say when she gives talks on the subject of neutron stars, that neutron stars are so bizarre that if you could stand on the surface of a neutron star, which you can't, the gravity field is so strong it would just flatten you, thinner than a pancake. But
Right.
imagine you had special magic powers that you could do that, okay? And you had, let's say, a baseball in your hand. And if you held the baseball, okay, with your arm parallel to the surface of the neutron star, and that baseball is at rest, it's in your hand, and you drop that baseball, by the time that baseball hit the surface of the neutron star, it would be traveling half the speed of light.
That's crazy. Yeah. But that's what we're talking about, folks. Yeah,
It's amazing when you think about it.
it is. And again, these things are observable. It's not that this is just somebody's fantasy worked up. These things are observable.
So Hayden, let's look at the question that we have in the chat and see if you can offer some,
Okay, so I'll read it again.
yeah.
Bill Schwam asks, why wouldn't it work to explain gravitational waves if you just included time delay in a scalar, Newtonian kind of gravity theory? And I'll admit, I'm not really sure what that question is asking, so maybe Hayden can elucidate.
My understanding about why it would work or wouldn't work is because not just mass contributes towards gravitational pull. Everything will experience some type of gravitational pull. So even light, which is made up of massless particles, photons, will experience gravity and produce some type of gravitational pull as well. So you have to take into account that, okay, there is some type of thing that is propagating gravity, and it should have some type of energy to it if it's propagating gravity and can propagate as waves. So that in and of itself should also have some type of gravitational pull to it. So because of those non-linearities, it will, and self interaction maybe is the right way to think about it. It will produce non-linearities, and the whole theory of trying to just put in a speed limit to Newton's laws is where the theory breaks down.
In fact, isn't one of the major tests of showing that, as far as we know, that the general relativity seems to be on the right track, was the deflection of background stars behind the sun during a solar eclipse.
Eddington. Wasn't it Eddington?
Yeah, Arthur Eddington. And so this was like 1918, I think it was.
Something like that. Yeah, it was just before World War One because he actually was captured as a spy for a while.
Well, that would have been just after World War One, you mean?
Okay,
Right.
yeah,
So,
right around in there
yeah.
somewhere.
When World War One started in 1914 to
That's
1918.
right.
So during a total solar eclipse, and it has to be total because you want to block the very bright light coming from the photosphere of the sun, you can observe stars in the vicinity of the sun.
Real close.
And if they're bright enough, you don't even need a telescope. You can see that with your eye during a total solar eclipse of the sun. But with a telescope, of course, you can photograph that region of the sun where the sun is. The moon is blocking the bright surface of the sun, and with a fairly long exposure, few seconds photographs, you can see some fainter star near the surface of the sun. And you can then look at that same star field when the sun is not in that location. So let's say at nighttime, when the sun is on the other side.
So
180
6
degrees
months
away.
later.
Yeah, 180 degrees away, let's say. And you can image that same star field. And when you compare those photographs, you'll find that the position of the stars relative to each other is not the same. The stars that were near the edge of the sun as viewed from the Earth at the time during a total solar eclipse has been deflected slightly. That is, in a slightly different position compared to when the sun is not there and you take a photograph of that same star field in the nighttime. So you can measure those positional offsets fairly accurately. Right? Assume there's instrumental effects you worry about and so on and so forth. But once you take all that into consideration, you can measure those deflections. But if you think of Newton's understanding of gravity, and you use, let's say, the idea that energy has mass equivalent to it, so you use E equals mc squared, then you could say, well, photons have energy, and that energy, I can think of that as mass. And therefore, when a photon passes near the edge of the sun, it's going to feel the gravitational field of the sun. This is not Einstein. This is using Newton, of course. So it's going to be pulled slightly towards the sun. In other words, it'll be deflected because of that gravitational interaction. But that deflection is not the same angle of deflection you get if you use Einstein's general theory of relativity, looking at the same star and the position where it is in both cases. The deflection is different. In fact, it's different by a factor of 2. And so when the experiment was actually done and the deflection was measured, they found that the deflection angle was consistent with the general theory of relativity, not with Newtonian's theory of gravity, Newton's theory of gravity.
Okay. That brings up a question I have then, if I can remember what it is. Is that one of the proofs then also that photons were massless? That they did not behave as Newtonian objects?
Well, if you
When
don't
they pass
think,
the
if you
sun?
don't use equals mc squared and you assume photons are massless,
Right.
then people wondered, well, they won't be affected by gravity.
Right. So if they are affected by gravity and it's Newtonian gravity, then they should have some small mass.
Well, once you equate, like from the special theory of relativity, so that's before GR came out,
Right.
if you equate rest mass with energy, then photons would have an equivalent mass associated with them.
Right.
And that's even though you can't bring them to a standstill to have zero mass, it's at some finite rest mass, they have zero rest mass. But if you can equate energy with mass, then you can equate, well, then gravity should affect them
Right.
in their pseudo mass that they have, the photons, and therefore cause that, they would
Okay,
feel the
okay,
gravitational
I get
force
it.
and then cause
All
it a
right.
deflection.
All right. And this, folks, is what happens when you get scientists in the room together.
Right.
Uh,
So in other words, there is a difference between the Newtonian view of gravity and its effect on light and what you get from the general theory of relativity and its effect on light.
right.
And in fact, what type of path, Hayden, does light travel then in curved space-time?
So are you looking for the specific term?
Yeah, let's throw that term out there so in case people hear it in some other
So
way.
yeah, the term for what the path that light would actually follow is known as a geodesic. So the way to describe a geodesic is people will compare it to like great circles. So if you take like the Earth, for example, you've got lines of latitude and longitude. Those lines of latitude and longitude are kind of your great circles that go around it. So like the equator going around would be a great circle going around the Earth. So your geodesics are kind of like that, and light will naturally want to find a geodesic and then stay along that. So, like going around the sun, the space gets warped around. It follows that geodesic. The geodesic says it's going straight, but then light wants to stay on that. And then from our point of view, it looks curved.
Right.
Right, so you can think of the Earth as a perfect sphere, which it isn't, but imagine it is. Then the only line of latitude that would be a great circle would be the equator.
The equator.
Any other, which means that the center of that line is the exact geometric center of the Earth itself. Any other line of latitude would not have the center of the Earth as the center, and so it would not be a great circle in that sense.
Right.
But all lines of longitude would have as their center the center of the Earth. So
Yep.
if you want to travel from, let's say, Seattle, Washington, over to, I don't know, Rome, then to save fuel, an airline would try to follow, at least as much as possible, a great circle, because that minimized the distance. So it's the shortest path in curved space. That would minimize the distance that the airplane needs to fly, and therefore minimize the use of fuel, and therefore it's cheaper for the airline to fly those type of routes.
And so the geodesic is essentially the shortest distance between 2 points in space and time.
Well,
or
the thing,
space-time.
yeah, and the thing to note is we're so used to thinking about locally around us, everything seems to be flat,
Right.
right? When we think about the flat Earth, right? If you're looking at the map of your city, you don't have to take in the curvature of the Earth into consideration.
Right. It's too small compared to the size
Exactly.
of the Earth.
And so in that case, you say the shortest distance between 2 points then from Euclidean geometry is a straight line.
Mm-hmm.
But if your space is curved, such the surface of the Earth or the surface of a basketball, then the straightest line, if you like, on that curved surface is a great circle, is a geodesic, and that's what a beam of light would follow.
I always like to describe it as it's the straight line through a curved surface.
Well, over a curved surface,
Over
if
a
you can
curved
think of it
surface, right.
that way, right? You're not like you're tunneling in another dimension.
Right.
You're trapped on that three-dimensional surface of a sphere.
Right. So yeah, it's the shortest distance in space and time that things can take.
In fact, you can actually see this quite easily nowadays. It's much easier there are websites you can go to like FlightAware and all this sort of stuff.
Right.
This sort of thing that shows you what's going on in terms of where is the position of planes right now at any given moment in time. And you'll see a lot of planes are up in the high Arctic.
Mm-hmm.
And if you click on them, they'll tell you where they started from and what is their destination. And they'll start like I said, like Seattle, let's say, and they're going to Rome in Italy. And yet they're in the high Arctic. And it's like, why are you flying there? On a map, you would fly east, right?
Right.
No, that's the longest route because the flat map doesn't give you the actual three-dimensional or the curved structure of the Earth itself.
Right.
In fact, it's essentially like a sphere. And so the flight that they actually follow is the shortest in terms of distance, and that's the one they want to take to minimize cost, obviously.
Yep.
So,
Yay.
yeah. But, gravitational waves, if you think of the Earth, which we mentioned already, Hayden, that's not a perfect sphere. So as it travels in its orbit around the sun, which, from Newton's perspective, that means there's a force, a sort of action at a distance, right, of gravity from the sun and the gravity of the Earth interacting with each other and maintaining the orbit that the Earth has. But from the point of view of the general relativity, Hayden, of course, that's not what we envision. What do we envision? Why does the Earth have the orbit that it does going around the sun? Can you explain that from a GR point of view?
So from the GR point of view, the Earth goes as straight as it can, just like light would do, and will also ride one of those geodesics that actually goes around the sun.
Right, so people often say, why does the Earth have the orbit it does? It's like the Goldilocks principle. It's just at the right distance from the sun, not too hot, not too cold. But then you could argue, look, if there was another planet that was on a different type of path, then that path may have been, for example, that it actually went into the sun and long since vaporized and became part of the sun, or it went around the sun like a slingshot effect and it had reached enough orbital speed that it's been flung out of our solar system.
Yep.
The planets that survive today that we see around us in our solar system are the ones, and that includes things like asteroids and so on, the ones that are on paths that are following the curvature of space.
Paths that don't take them into the sun or out into
yeah,
the
they're
infinity.
bounded orbits in that sense,
Right.
as we would say.
Right.
Everything else is long since gone, right?
There you go.
And
Okay.
for analogy on that, it's almost like, once again, getting back to like a piece of rubber. If you had a piece of rubber that's stretched out on the frame, you can think of it as the surface of a trampoline again, and you were to roll a marble. Back in the old day, when I was a young kid, we used to play marbles. That was a big thing back then. So if you like get a marble that's moving in a straight line, it'll roll across the surface of a trampoline and go off the edge of it, let's say.
Right.
But if there's somebody standing at the center of the trampoline and you tried the same type of experiment, even if you don't have your marble initially moving towards that person, let's say you move it in such that they would miss that person by quite a distance, that marble will turn around, that marble will actually follow a path of the curvature of the surface of the trampoline. And that path may be that the marble actually hits that person, hits them on the feet, let's say.
Yep.
So that marble deviates from a straight line path. So from somebody watching above, not understanding what's going on, they may say, hey, there must have been some force of attraction between that person standing in the middle of the trampoline and the marble, such that that force caused the marble to deviate from the apparent straight line path.
Yep. You mean it didn't? Wait.
So our whole notion then, Hayden, of gravity and getting away from the idea of force, I mean, why do we still teach Newton and the universal law of gravity in school if general relativity is a better description overall of gravity?
Because I would say that's twofold. General relativity is hard and Newton is still really accurate. You can still land on the moon without touching general relativity once. You don't need to be all that accurate as long as you're staying far away from heavy masses, far away being about like the orbit of Mercury, heavy masses being on the order of the sun, and not going very fast. So for most instances, you don't actually have to use general relativity in day-to-day life. It is when you want really precise stuff or you want to get really close to things that you start needing to use it.
I kind of wish we'd prepared a slide for this. Yeah, we could show you the equations, the math for general relativity. That is one of the reasons, because holy crap.
Well, here's the way you think about it too. You can say, well, you learn Newton's laws of motion.
Mm-hmm.
That separates our time from the laws of Aristotelian physics.
Okay.
And so that brings in the idea of basically a friction that you, right, in the physics under Aristotle back in ancient Greek times, let's say 2,000 years ago, to keep an object in motion, you had to apply a force on that object. Once you got rid of that force, then the object would slow down and come to a stop. And of course, we know there's friction you have to worry about, but if you don't understand friction, you might assume that a given amount of force will give rise to a certain velocity.
All right. Well, I mean, how can you say there's a force there when there's nothing pushing on it?
Right, and so it's our common sense, right? It's not made
Right.
up. It's not like someone like Aristotle would make all this stuff up.
Right.
It's just that your life experience is, if I want to keep a ball rolling down this gravel road, I need to keep pushing on it or it'll slow down and stop once I leave it go.
Right.
And we know that if you take that into an environment in which there is no friction, you can do this through a thought experiment, for example, we know that that's not the case, that a force gives rises to acceleration. And so once an object is moving relative to you, that object will maintain that velocity, as we say. That's a constant speed going in a certain direction, unless there's some other external force that operates on that object,
Unless you give it a push.
right? So you initially get it going, and then when you no more force, you give it an impulse, as we say.
It'll keep on going.
It'll move in a constant velocity so long nothing else acts on it, no other forces, nothing.
Right.
And so that's a thought experiment in the sense that we don't operate in that environment day to day,
Right.
where we can neglect friction totally.
Mm-hmm.
There's friction all around us. And so that's the problem in trying to, uncover the fundamental nature of what happens in physics, for example, is we seem to always be going down this road is, let's get out of my environment that I'm so used to. Let's go to places where I'm uncomfortable, even if it is a thought experiment, to see maybe I can get at the more fundamental nature of physics itself.
Right.
Now, Hayden, you mentioned Mercury. So Mercury turns out to be an extremely important planet in our solar system when it comes to general relativity. Can you explain a little bit about Mercury's role in GR?
So Mercury's role in GR is that it is basically just close enough to the sun that if you use purely Newtonian gravitation, you, the path of Mercury will slightly deviate from what Newton would predict under general relativity. I think the order of the prediction is somewhere along 1 arc second of length or 1 arc second around its radius per 1 century. So it's a very small difference, but it is a large enough difference that it was actually measured, and scientists had actual legitimate concerns about it and thought that, okay, if this theory of gravity is correct and Mercury is clearly not following the path that it's supposed to be following, we must have another planet there. And people looked and looked for this other planet. It eventually earned a name. Its name was Vulcan. And there were supposed sightings of it, probably just sunspots. And then after enough time, people realized, oh, hey, Vulcan's not there. And that is another test that you can actually say that, no, Newtonian gravity needed some type of update. And then that update came in the form of general relativity.
Right, so there is a case in point there, therefore, where you have clear violation of the observation, right, with a fundamental understanding of the physics. So if you in a century, in 100 years, the deviation, as viewed from the Earth, of course, on the order of about 43 arc seconds, by the way, because one forgets all these numbers, right?
Absolutely.
Obviously. So it's 43 seconds of arc per century is the deviation.
Okay.
And that means that the laws of universal gravity, as described by Newton, when you compare that to observation, there is a mismatch. In fact, if you observe really carefully, even Venus is going to have this type of precession of its closest point to the sun. Right?
Mm-hmm.
So it's perihelion distance. And even the Earth has. In fact, every planet technically would have that. But the difference, that is, the effect becomes smaller and smaller and smaller as you get further and further away from the sun.
Right.
So it is most observable for the closest planet to the sun, which is Mercury. And as you mentioned, Hayden, people hypothesize, well, if the orbit of Mercury is not correct, as based on Newton's understanding of gravity, there must be an additional force somewhere at play here. And one way of getting that additional force is to pretend there is
A planet.
another planet.
And we have a question, and I was going to bring this up, so I'll go ahead and interject the question.
Yeah.
Can you, Wintergreen asks, can you explain arc second, please?
So Hayden, you want to do that?
So an arc second is a unit of measurement around a circle. So if you have a circle that can be subdivided into 360 degrees, you then can take one of those wedges and further divide it up into 60 increments. And one of those increments is what's known as an arc minute. Then you can take an arc minute and further subdivide that into 60 more increments, and then you'll get something that's an arc second. So an arc second would be
3,600th of a degree.
Yeah.
So there's 3,600 arc seconds in 1 degree.
so it is a very small deviation from what Newton would predict, but that deviation, like I said before, it's small but not immeasurable.
Yeah.
Right. In fact, it's enough so that people actually took the time to look for this new planet that should exist somewhere between Mercury and the sun.
Which is one reason some of us are a little skeptical of all these claims that there's a planet out in the Kuiper Belt because of measurements of gravity.
Well, the only thing to say there is this deviation of Mercury's orbit from
Is
Newton
different.
is different. It is
Yeah.
solid. I mean, it is well within the uncertainty of observational measurement.
Absolutely.
And the problem is, of course, you can easily hide a planet close to the sun, right?
Yep.
Because who's going to take a telescope and look near the edge of the sun, especially if there's not like a total solar eclipse happening at that moment where you are
Right.
on the Earth. And so you have to be extremely careful to do this. I mean, you have to look just as the sun sets in the evening, scan very rapidly around that general area in the west, and just prior to when the sun rises, scan around that area in the east. But if you wait too long, you might accidentally point the telescope up to the sun, then you're blind.
Then
right?
you're blind.
Then your day's over in terms of looking for the planet using this method. And so people did these careful searches and never found anything.
Right.
To the point where they basically said there is no other planet closer to the sun than Mercury. There is no object large enough. And, there could be a small asteroid or a comet. In fact, lots of these objects do get closer to the sun, comets, for example, but they would not have the mass required to cause the deviation in Mercury's orbit. That's the point.
Right. That's the problem.
Right? You need something massive enough, and therefore it's going to be potentially more observable to cause the change in Mercury's orbit. And that was never discovered. And we know today it doesn't exist. And we've searched that space well, and we know there's no other planet
Right.
that's between the sun and Mercury itself. In fact, wasn't it Einstein, Hayden, that mentioned by talking and in his writings, that is when he actually came up with a prediction for the precession of Mercury's orbit based on the general relativity, that he knew at that moment that GR accurately described nature more so than Newton's law of gravity.
I think that was one of his first tests before he actually published it. I do not remember if he actually included that in his first paper or not.
Okay. So I'm going to get into a little of our semantics here. Why do we call it, if general relativity is better, why do we call it the theory of general relativity, and Newton, which is worse, the law of universal gravitation? So why do we call the better one a theory and the worse one a law?
Do you have any opinion on that, Hayden?
The only thing I would say is I still refer to Newton's as the Newtonian theory of gravity as well.
Okay.
And kind of in physics, there isn't a lot of difference between theory and law, because a theory isn't like what a layperson would say theory as. Theory is pretty well accepted as fact. If it's not accepted as fact, it's not a theory, it's just a hypothesis.
Right. And that's what I was getting at, is we use theory in a different way than the average, person is going to. For us, it's not a guess or an opinion. It's something backed up by observation. It's backed up by facts and a body of facts. And, it causes confusion.
And the other thing, of course, is the fact that when a theory has been around long enough, and long enough is debatable, it could be several hundred years, then the theory becomes a law. So you need a lot of time where the theory can be tested and tested and tested and tested. General relativity's only been around for 100 years.
Right.
And I say use quote unquote only, but
Yeah.
it's been around for 100 years, and people are still doing tests related to general relativity today to see if it's consistent with the GR itself. Where Newton's law of gravity has been around since the 1600s.
Right.
And so I think elevation to a law is when something has been around long enough that people have no doubt that it's correct. Then it gets elevated into this word law. But I mean, these are all human-made constructs. Obviously, They're just words.
They're just words.
In fact, when you know about general relativity right away, you would say, well, it's not a law then, Newton, because we know it's wrong.
Right.
It may give you predictions that are very close to what GR gives you, but it's wrong. And in certain regimes, it's very wrong.
Very wrong.
And so it's not in that sense, but we still get away historically by using the term the universal law of gravity, these kind of things.
Right.
But that's what's happening here. It's more of a semantics use of English, not really doing it properly, historical reasons.
Right.
That and the fact that Newton has been around since the 1600s in terms of his published work.
And it's accurate enough. So we're not going to just throw it out.
Yeah.
It's accurate enough.
Well, the other thing is we talked about that when you first learn this in school, let's say as a young child, it's much easier to comprehend the Newton's version of gravity. And I wonder, should we stick this caveat in there when we first teach people about the universal law of gravity? By the way, this is really an approximation.
Right.
The better explanation that we have is the general theory of relativity. It's highly more complicated and mathematical, But just to let you know that, that with
Well-
Newton, we can, land probes on Mars, for example. We don't need general relativity.
I'll put it this way: for Newton's law of gravitation, you can sit there and use multiplication and division and crank out a numeric answer. Whereas for GR, you've got to use tensors and n-dimensional tensors and all sorts of calculus and linear algebra to crank out the answer. So the two are vastly different mathematically. And Bill has brought up some more points. He says, thanks regarding the effect of gravity in light and the factor of 2. For instance, that's interesting. I suppose only mass would be a source of gravity for Newton. And I wonder how much of the gravity waves coming from merging neutron stars is due to the convected gravitational energy density.
Now, I can say a little bit about that. When the
Okay.
first LIGO detection that was made in 2015, that was from two black holes that merged together. And these black holes each have tens of solar masses each.
Mm-hmm.
And if you take, I forget the exact numbers, but if you take the two black holes prior to merging, and then you look at the mass of the black hole, that is the combination of the two, the difference in the mass was on the order of something like 2 to 3 solar masses difference. So in other words, you could take a 40 solar mass black hole and another 40 solar mass black hole, merge them together. And instead of having a single black hole that is the sum of those two masses, so it would be 80 solar masses, you find out that the mass of the black hole that's produced is 77 solar masses. So you might ask, where did those 3 solar masses go? It's missing. They were the mass that was transferred into energy that went in the form of gravitational waves.
Right.
So it took a tremendous amount of energy. You take E equals mc squared, you put a mass of 3 solar masses, see how much energy you get out of that sucker. It's enormous, right?
Right.
In other words, space is extremely stiff. It takes a lot of energy to shake it.
Right. That's what I was going to bring up is that this means, this is why we don't see the effect of gravitational waves in everyday life is because space and time are extremely stiff. They don't shake. They don't vibrate readily. You've got to put a lot of energy in there.
Exactly.
3 solar masses of energy shakes on the order of, 10 to the minus,
10 to the minus 10 meters or so is a fraction the size, but 1/10,000th the size of a proton.
Right.
If you think of a proton as a particle, which is another discussion.
That's another day.
That's another podcast. Right? Yeah, so these are incredible amounts of energy that need to go into the generation of these gravitational waves such that we can detect them here on Earth.
Right.
And this is using the best technology that we have at our disposal today. This is front of the line type of really pushing the envelope in our ability to detect these type of things. That's why, people have been trying to build gravitational wave detectors, as Hayden, you can mention such of the early experiments that were done using a bar, for example, of aluminum, a cylinder of aluminum. It's taken basically decades for us to develop the technology to the point where we can finally detect some of these relatively strong sources.
And a lot
Strong,
of false
quote,
detections.
unquote. And into the future, that technology is only going to get better, and that allows us to detect weaker and weaker sources.
Right.
So, Hayden, do you want to mention what I just alluded to about our early attempts to detect gravitational waves and what that was all about?
So yeah, like you said, there have been attempts to try to actually detect gravitational waves since probably about the 60s. The first real attempt was something called Weber bars, which were just aluminum bars that would, if a gravitational wave passed through them, the length of them would expand and contract a very small amount, since that's the way gravitational waves interact with the material around them, is they will distort space-time, and they'll do that by expanding and contracting space-time. So these Weber bars would actually expand and contract a very small amount, and there would be sensors around the antenna to actually try to measure that. And it turns out at length scales about 2 meters, which was the length of these bars, it's just not nearly sensitive enough to actually detect that. Then in the 70s, people had ideas to use lasers and laser interferometry to actually try to measure it. So basically what you're doing with the lasers are just a different type of measuring stick, and you can just make something a lot bigger. So now LIGO can measure something over kilometers instead of just 2 meters. So now you have a lot more distance that you can actually measure a changing distance over. So your machines don't have to be as sensitive since you've got something like that. But so yeah, this has been going on since the 60s and 70s. And the first confirmable detection is just recently in 2015. So there's been subsequent detection since then. So we're still in the very early days of actually being able to make these detections. It took so long to get the technology to a point where it can make these detections. So now from here, the technology just gets better and better, and then you can make more and more detections, hopefully to the point that one day you don't just see these random blips. You can actually see these steady sources.
Right.
I mean, the other thing to note is when you think of people doing experiments like back in the 60s to detect gravitational waves, that you just don't know what sources are out there in the cosmos. And so you can estimate, whether or not your estimate is based on being very liberal in your estimates. That is, the signal is a lot stronger than what it really would be on average from different sources. That I might have a shot at detecting this thing, so let me give it. And if I don't try, nobody tries, you never know, right?
Right.
It's like listening for extraterrestrial intelligence from signals from space using a radio telescope. If you don't go and observe and do the experiment, how do you know if there's not civilizations abound everywhere, right? That's transmitting and that we'd be able to easily pick up.
Right.
You don't. So you do the experiment, it didn't work, even though it was reported, it was a false positive, and as the history goes, but that's okay because we've detected then the gravitational waves from LIGO, and then you can work backwards and say, okay, what was the chance of this bar being able to detect it in 1960? The chance was 0,
Right.
essentially. So it wouldn't have worked, but we didn't know it at the time, right?
And in fact, we've got a question about that. And do either of you have any idea the rough magnitude of path length changes at LIGO? Joseph Langenwalter asked that.
Yeah, so it's on the order of 1/10,000th the radius of a proton.
Okay. So let's see. Yeah, that's about 10 to the minus 20. So decimal point, 19 zeros and a 1.
And the problem in all this is building the technology up to the point where you can detect such a very small alteration in the length or contraction of space.
And
that's based on basically laser technology, sending lasers down these long arms of 4 kilometers in length, reflecting off of mirrors, and they go back and forth several hundreds of times. Ultimately, you combine that light and you tune the lengths of these arms by moving ever so slightly the mirrors, so that the light then, when it goes down these 2 separate lines that are at right angles to each other, like a giant L, and you tune it so that when the light recombines after passing back and forth all hundreds of times, it tune it in such a way that the light is completely out of phase with each other.
in other
so
words,
you get complete destructive interference.
right. So you see black.
You see nothing, no light at all. And if the positioning of the mirror changes ever so slightly down one of these arms, then all of a sudden the light is no longer perfectly out of phase with each other, and then you'll see some light. So you can have like a photocell waiting for detection of light.
And on that note, I'll bring up that, that's interferometry, and something we actually put our undergraduate students through is seeing a much less sensitive version of this. But you will see this interferometry technique if you just come and get an undergraduate degree in physics.
And this gives you an idea how sensitive these experiments have got to be.
Mm-hmm.
These lengths of arms are in a near vacuum condition. They're 4 kilometers long, and there's 2 of them at right angles to each other to form a giant L, as I mentioned.
Right.
Now, they are sensitive to any type of vibration. In fact, a crow, and this actually happened. Okay, I'll be more specific. A raven picked on the outside of a cooling tube on the surface, and that was detected by this experiment. It caused enough vibration in the system that it set off an alarm, and they saw on camera there's this raven pecking away at the cooling, right?
tube.
Aluminum pipe. And that created enough vibration. In other words, what that really means is it's hard to run this experiment on the Earth because of the natural noise, as we'd say, whether it's a 18-wheeler going down the nearby interstate, or it's a tremor, or a moderate earthquake, or any type of earthly influence will cause noise. And so the real advance that was made in the middle to late, like 2010 timeframe was to do the engineering so that these mirrors are completely isolated as much as possible from the earthly environment, to the point where any shaking in the mirror was actually caused by gravitational waves passing through and not something inherent to the earth itself.
And that brings up the point, how do they still know then that it was gravitational waves and not?
Easy. Instead of having one detector, why not make two of them for double the price? You
For
put
double
one
the
in
price.
Louisiana, you put in Washington State. And both of them detected the first gravitational wave, and they detected in a separation of milliseconds, which is exactly how long it would take light, which is what gravitational waves travel at the speed of light, to go from one of those experiments to the other. They detected and the same wave pattern. So you knew it couldn't be some earthly noise that was only available or inherent to one detector. So by using multiple detectors, then we can isolate, if you like, the signal, and knew that it was coming from beyond the earth.
We don't like doing things with one detector.
No, you put yourself in a bad spot.
Absolutely. Absolutely.
Yeah. But Hayden, I guess we're at the end of our podcast. That hour went by. It must be the time effect.
Time change.
And,
Yeah.
So
Time
My clock
dilation.
says we still have some more time.
Time dilation. You must be
I'm
moving.
farther away than you.
you
That's
must be
it.
moving faster than us.
Anyway.
Anyways, so we will wrap this up. So thank you all for watching and listening to this podcast. Don't forget that if you're interested in physics, if you're interested in math, or any other field in higher education, please join us here at the University of North Dakota. You can take classes on campus, of course, in person, as we say, or you can also visit us online, Robert.
Absolutely.
And-
Use that technology.
Yeah, so if you happen to be at a base in Antarctica and you're passing the time, one of the things you do is get an online course from UND.
Absolutely. Yeah.
As long
let's
as you
do
have an
that.
internet and you can interact once in a while, hey, it works. And with Starlink satellite,
Right.
we all have internet, don't we, here on Earth now?
Yeah. We won't go there.
Now, our next podcast will be Tuesday, November the 14th at 3 p.m. Central Standard Time.
Standard time.
And we will have a special guest. Dean Smith will be joining us, and he will be telling us what's going on in the winter skies that's rapidly approaching here in North Dakota.
Yeah.
But before we leave you, we always end with a quote. So today's quote is from Jocelyn Bell Burnell, who was the discoverer of pulsars, which is a way of detecting neutron stars. And we talked a lot about neutron stars today. And the quote is this: "Pulsars are in an ideal part of the universe to test Einstein's theory of relativity. So far, it's holding up well. They may even one day act as navigational beacons for spacecraft. I'll never tire of them. They really are the most extraordinary objects." And with
Nice.
that, thank you very much for watching.
See next week, folks.